Okay, then we start the recording and we start the colloquium. So good morning, everyone, for this colloquium on a somewhat unusual topic, but we're happy to have Professor Gary Steele from Delft to give the colloquium today. So Gary did his undergraduate studies at McGill University in Canada, and then did his PhD at MIT in the US, where he also spent 7 more years as a research assistant. He then came as a postdoc to Delft University in the group of Leo Kouwenhoven that many of us, of course, know. And since 2015, he is tenured as professor at in Delft. As a PhD, he did studies on mesoscopic physics, quantum Hall effect, later also on nanotube spin physics, electron interactions in quantum dots, and as a PI in nanotube superconducting circuits and 2D materials, of which we will hear more in the talk. He has been very successful in acquiring personal grants. Started with a VENI in the Netherlands and then with a VIDI in the Netherlands, and also a few years ago he had a ERC consolidated grant on quantum optomechanics in 3D. So today Gary will talk about this subject, and we're interested to learn about it.
Good, great. First, so I think, let me see if this works. Will technology work? That's always the question. So I think if it's good, you can see my screen. Great. Okay, so great. So first of all, thanks to Patrick and the committee for inviting me to give a talk. This came about actually because there was my postdocs were looking in the March meeting website a while ago, and they saw some talks that were very much related to some work we're doing in the group. It's a little bit in this direction of quantum sensing, and then they were like, wait a minute, this is exactly what we're doing. And then we looked at the author and we were like, who is this person? And it turned out to be someone from Stanford who was working on who's actually trying to use these for applications in dark matter searches for axions. And then I was like, oh, that's very interesting. I wonder what this is all about. And so I reached out to Patrick, who I knew, who was my roommate in our house for a few years back in the olden days at MIT. And that's actually how we got started talking. And then the idea is I want to give you guys today a little bit of a sense of what type of stuff we do in my group. We're sort of part of this quantum movement of these days, and I'll tell you a little bit about what this is, how it works, and what we do with it. So I want to maybe also start a little bit with where I am. So I'm part of the Quantum Nanoscience Department in Delft. That's the Department of the Applied Physics faculty. Or applied physics, yeah, indeed, faculty, applied sciences faculty. We have 3 sort of research directions, sort of quantum matter, where we look at quantum materials, quantum sensing, and quantum transduction, which are kind of not so different from each other. I think it's always important to advertise for hiring. So if you know anybody, if you happen to know anybody interested in quantum sensing or quantum applications, maybe also from your guys' field, we are still actually looking for people to join our team. Quantum in Delft is getting really big. Actually, quantum in the Netherlands is getting really big. So I find it useful to sort of try to show my idea or my understanding of where we sit. So there's a huge growing quantum community in the Netherlands. Recently, there was this national initiative called the Quantum Delta was started. Under that national initiative, there's a ecosystem called Quantum Delft. And in that ecosystem, Quantum Delft, there's people working on quantum science, quantum technology, and in quantum industry. And we sit sort of more on the side of this quantum science. QTech is sort of bridging quantum science to quantum applications, quantum commercial work, and then there's this whole gaggle and zoo of new companies coming up in Delft, working on really quantum industry applications. So maybe to tell then a little bit about my group. So let's say I want to, so in sort of in the context of this picture, you know, what we work on is sort of two topics where you can describe what we do in terms of two main topics. The first I'll call quantum sensing, and that's where you make devices where we try to either, this is sort of a fun, I'll get into more detail about this later. We either try to sense with quantum objects, or we try to sense at the quantum level, really at level h bar. And then we have another topic, which I'll touch on briefly, where we try to do quantum simulation. And there the idea is to build quantum simulations, quantum circuits or quantum devices that emulate a Hamiltonian thereafter. And in our group, we do both of these using superconducting circuits. So these are little pieces of metal that we pattern, superconducting metal that we pattern on a chip in the clean room. And this is, I'll tell you more in detail, actually. I'll try to give an introduction to you how these work and how we make them. So if you go walk into my lab and open things up to give you a feeling for what the type of things we do, this is what you'll see. This is a typical picture of one of our experimental setups. This is a dilution refrigerator. This sits in a huge vacuum can. This plate here is cooled to 10 millikelvin, and we have all of these wires coming in. There's all these microwave lines that we use to interrogate our device. They come down, they go into our devices, either mechanically shielded or mechanically isolated or magnetically isolated, for example, from the environment. And then these signals go back up and we amplify them, and they come back out into our equipment at room temperature. And that's a little bit sort of a feeling for what it looks like in the lab. And then what we do, part of our work is building these setups in the lab. The other part is building the devices we put into this fridge to measure. And these consist of these little wires of superconductor, which we sometimes wind up into an inductor. Sometimes we make them into a giant capacitor, and sometimes we actually do something else, which is make a device I'll tell you more about called a Josephson junction. And we have a bunch of different directions. We have sort of two main directions, one where we look at more of the circuits on their own and applications of the circuits, and the other where we use these circuits to try to detect mechanical vibrations. So very quickly about quantum simulations. So yeah, the basic idea in this field, I want to get this out of the way and move on to quantum sensing later. But the idea is that there's certain problems you want to solve in physics that are difficult. Somewhat difficult problems involve things like quantum chemistry calculations. Much more difficult calculations, well, it depends who you ask, involve things like explaining why high DC materials are superconductors. And the idea of quantum simulation is that you have some hardware, which I'll tell you more about later, but it's basically these little circuits on a chip. And we want to try to solve this problem with the hardware. So one approach is what I'll call digital simulation, where you take this Hamiltonian you're after, you encode it into gates, you take your hardware and approximate it as a qubit, and you can do something called digital simulation. And but that's sort of something where people like Google and IBM, who have 53 qubit devices, can start to make some serious impact. But we're looking at it from a different angle, and there what I'll describe is, well, say is that it's sort of the idea of analog simulation, where instead of trying to perform this mapping, we try to directly build hardware that mimics the Hamiltonian thereafter. That's one of the research directions that we pursue with these devices. But then the main topic I want to talk today about is quantum sensing. And I want to start with trying to describe to you what it is and why I would want it. So there's actually not a particularly good definition of quantum sensing. Um, so there's sort of a working definition. One working definition is that it's basically sensing with something that is quantum. But then if you want to say what is quantum, you have to get into a bit of an interesting discussion. Atoms are definitely quantum. Photons are probably quantum. I'm not sure whether light itself is quantum. I actually personally believe that I am probably quantum, but I don't know whether that qualifies me as a quantum sensor. What I want, maybe the question I would rather like try to answer is whether or not quantum can be useful for something in sensing, and in particular whether quantum can be better than classical. First, though, I want to show a very nice example recently of sensing with quantum stuff, and this is a work done by actually someone, Tim Timanu, who works in QTech, and they recently had a very nice result where they used a quantum sensor. This is an NV center spin, and this thing is sitting in a lattice of atoms, and using this NV sensor spin and sort of quantum control techniques, they could map out the position of a whole bunch of nuclear spins nearby and build a reconstruction of the nuclear spins in space. So this is an example where it's pretty clear that the thing you're sensing with is quantum, and that qualifies in some senses as quantum sensing. I want to maybe ask another question. Really, can we draw an analog of a quantum advantage with sensing? So for that, I want to look at the following example. So I'm going to consider a particle in one dimension. A particle in one dimension has a momentum and a position. I can describe it completely by a momentum and position. And what we often like to do in quantum optics and field I'm working in, then we like to draw this on a phase quadrature plot where we draw the state of the particle as a point in position and momentum space. And now the question you can now ask is, classically this is a point. Classically, I can determine this point to infinitely high accuracy. There is no limit on how accurately I can determine the position and momentum of this particle. And of course, in quantum mechanics, that's a little bit different. So in quantum mechanics, actually, there is this Heisenberg uncertainty principle, which states that I cannot simultaneously, determine the position and the momentum of the particle. And the uncertainty in the position and the momentum of the particle must always obey the Heisenberg uncertainty relation. So actually, if you want to take it really quite literally, based on this argument, I would even suggest that it's actually fundamentally impossible to do better than classical sensing. And so you might say that there is not really such, even it's sort of silly even to talk about a quantum advantage of sensing. And I think that's probably true, actually. So, but sensing at the quantum limit is actually already challenging and also can be exciting. And I want to give an example of that. So this is an example of from the field where I work with the mechanical work that I do. This is an example of something called Optomechanics. And that's where people use laser lights to measure the position of a mass. So this is a cartoon showing a mass on a spring, a mirror on a spring, and then a second mirror over here. And of course, the idea is that using the interference of the light inside this cavity, I can sense the position of this mass accurately by looking at the amplitude or phase of the light that is coming back out of this cavity. This is actually, of course, the entire principle of gravitational wave detectors. This is the whole idea of LIGO. And actually, in my field, I interact quite a bit with people that work on the topics of sensing limits in LIGO. Now, there's a very nice way to analyze how sensitive you can be to the position of this mirror. That will bring us to something called the standard quantum limit. And so if I look at the total noise that I measure when I look at the laser field coming out, I will see some value, and this value will partially be from the noise in my detector. If my detector is quantum limited, then as I turn up the measurement strength, in this case, a laser power, then this noise will go down. This is actually just the noise, the shot noise of the laser going, the relative shot noise of the laser going down as you turn up the power. Now, there's something very fun which happens, which is that if I turn up the power of my laser sufficiently high that I can measure the 0 point fluctuation noise, then actually there's a second curve that enters into the noise I measure in my detector, and that's something called quantum back action noise, and that actually increases as I turn up my laser, and actually this has an origin in the fact that my laser is exerting a radiation pressure force on my mechanical resonator, and so as I turn up the power, actually the force on the mechanical resonator, there's a statistically fluctuating force from the shot noise of my laser. And so although the relative shot noise, amplitude noise of my laser goes down, causing this curve of detection sensitivity to drop, actually the mass itself actually experiences a random fluctuating force from the shot noise of my laser. You can combine these two, and that gives us this curve here. This red curve is that describes, this is the standard quantum limit of position detection in something like LIGO or in a mechanical resonator in this optomechanical setup. And one thing that is commonly discussed is that this looks like heating. Over here, it looks like it is a bit like heating because my mass is actually experiencing a random fluctuating force. This is sometimes called radiation pressure heating or the radiation pressure shot noise limit. But actually, the noise I'm imparting on the mass, this fluctuating force, is actually purely quantum noise. It comes from the collapse noise of my detector sensing the outgoing photon field. And what's very interesting is that it's not heating, and if you actually measure the noise very accurately, you can undo all of this noise and relocalize the position of the mass to the Heisenberg limit. And that's something that has been done most recently by a collaborator of a colleague of mine in Copenhagen. Okay, so now, of course, one of the challenges on Zoom is I have no idea. I cannot see any of you, so hopefully you're all with me. I will try to guess whether or not you're following me. But I will now switch gears a bit. So this is a little bit. I've tried to sketch a little bit of background of where the applications are in this. And now I want to show you a little bit, give you a bit of a tutorial on what we do in the group, how do we do all of these experiments with the superconducting chips. And I want to, in particular, try to describe to you how we build photons, atoms, and quantum amplifiers using superconducting circuits. So the first one is photons. I'll start with photons. Photons for us are actually pretty easy to make. Photons to people like me in circuit QED are basically LC circuits. So if I draw an inductor and a capacitor, and I can make these on my chip, then of course the equations of motion that describe that are a second order differential equation, just like a mass on a spring. There's going to be like the potential energy of the mass on the spring, there's going to be energy stored in the capacitor, and like the kinetic energy of the spring, there's going to be energy stored in the inductor. Now, because of quantum electrodynamics, I am basically allowed to replace this Q and this I with operators. Because of quantum electrodynamics, the charge on the capacitor and the current in the inductor do not commute. And actually, I can just freely quantize this equation, just like I would a mass on a spring. And what I will get, of course, is the spectrum of a harmonic oscillator, which in this parabolic potential, which could be the charge on the capacitor or the charge on the inductor here, the current in the inductor. I will have this ladder of quantized states where these states are all spaced by the same energy spacing, h bar omega. And then the words I use are that the number of photons is equal to the excitation number of the circuit. So that's, let's say, the mapping of things that we can make in the clean room to a particle, a fundamental particle being a photon. And what's important for us in practice is that if we want this harmonic oscillator to really be quantum, we want to make sure that the temperature of the system we're working with is much, much lower than h bar omega, and that prevents that allows us to know with certainty that if we do nothing, the system is in a well-defined quantum state and the ground state. And that means that at 40 millikelvin, so to give you a feeling, this mapping of 1 gigahertz maps to 40 millikelvin. And so we typically work at 10 millikelvin and about 5 gigahertz to satisfy this condition. Okay, so this is what our photons look like in practice. You can make them literally by making a capacitor and inductor, and that's something we do sometimes. This is actually a spiral inductor, which and this is a parallel plate capacitor we make on a chip. This is one approach. Another approach is to do this using a coplanar waveguide, where now this is like a Fabry-Perot cavity for microwave photons. And of course, that also maps to an inductor capacitor near one of the resonance frequencies. Good. So we have photons, but we want to do more than just photons because linear physics is not super exciting in quantum mechanics. And actually, of course, what we really like to do is to make an atom. And let's say the important difference between an atom and a photon, from our perspective at least, is that an atom is a system which has an anharmonic energy spectrum. In particular, the transition frequencies from 0 to 1 is different than 0 to 2, and this allows you actually to program quantum states of 0 and 1. And the reason is that if I try to drive a 0-1 transition, I always stay within the 0-1 states because I cannot go up to 0-2. And that's the problem with the harmonic oscillator. If I start to drive 0-1, then before I make it all the way up to 1, I'm already starting to drive transitions from 1 to 2. And so to make an atom on our chips, we need to have these not to be the same transition frequency. That means we need nonlinearity in our circuits. And so the question is, how do we get nonlinearity in these circuits? So if you just go to undergraduate physics, a circuit element that we are very familiar with, of course, is a nonlinear circuit element we all probably remember is a diode. A diode is ideally a rectifier. And then you could ask the question, could I just put a diode into my circuit and get this anharmonicity? Well, it turns out that you can't, and that's because we need a combination of two things. We need to have the 0-1, well, actually, what we need is this condition here. We need the difference between these two transition levels to be larger than their spectral line width. And so that means we need a very unique combination of very strong nonlinearity with very low loss. So how do we do that in practice? It turns out that there's a very fun way to do that, and that works by just taking two superconductors separated by an insulating barrier. This is a problem that was analyzed by Brian Josephson in the 1960s, I believe, as a PhD student even. You analyze the quantum tunneling problem from this. This is done very elegantly by Richard Feynman in the Feynman lectures. And it turns out that you can derive, you get an interesting result that the current and voltage are determined by the difference in the superconducting phase of the wave function. So this is all fun and cool physics, but what's very useful for us is that actually, if you look at these relations, it turns out that the Josephson junction in the circuit provides exactly what we want, which is a very low loss and a very large nonlinearity. This is what they look like in practice. We make them in the clean room by evaporating aluminum at 2 different angles and doing and oxidizing the aluminum in between those 2 steps. And what happens is that you have a piece of superconductor here, which is all connected together. And there's another piece that sort of rolls up over the edge, and in between these 2, which is something you cannot see here, there's a little 1 nanometer thick tunnel barrier that separates the wave function on the 2 sides. And that's, so if you do that, actually, if you analyze this, this gives exactly what we want. So we have, if we have an LC circuit, we have a harmonic oscillator, a parabolic potential. If we put this Josephson junction in, it turns out it's exactly a cosine potential. And that's exactly what we need. It turns out that there's a cosine potential with very low loss, and that gives us what we need to have this separation, spectral resolution of these 2 different transitions. Good, and then there's one more thing I want to introduce that we can do on the chip, and that's related to sensing. The cosine potential of the Josephson junction actually maps it directly to a rigid pendulum. So Josephson junction is sort of basically like a quantum rigid pendulum, which also can spin all the way around the top. If you have kids or have gone on a swing in your life, then you have actually probably made use of a process called parametric amplification. And there the idea is that if you can modulate in this case, you modulate the moment of inertia of the spring just at the right frequency and just the right phase, then you can get parametric gain. And this is actually a plot that my students in my undergraduate course, computational science course, computed recently numerically in their problem set. And so if you get the gain, the phase right, you can get gain. And it turns out that if you get that gain large enough, you can make this a quantum limited amplifier. So how do we do that in practice? How do we swing the legs of our Josephson junction? We do that by actually splitting our Josephson junction in 2. And what that does is it makes more or less an Aharonov-Bohm interferometer for the superconducting wave function. And that means that I can actually cause a result, I can get a quantum interference of the current on the top and bottom arm of this loop. And that allows me, with a magnetic flux through the loop, to change the critical current. And it looks like this. So this is a critical current, a cartoon of a critical current of a squid. The current changes over an incredibly small magnetic field. For example, a 10 by 10 micron loop is 20 microtesla. And for that, there are applications for it, like flying it in helicopters looking for oil or trying to measure currents in your brain. So what we do is that we take this little loop. It turns out that the Josephson inductance, it is directly related to the critical current. And so if I can change the critical current, I can change the inductance and I can change the frequency. And that is going to allow me to swing the kids' legs. And so this is showing a plot of the frequency of such a squid cavity, we call it, which is this superconducting quantum interference device of these 2 junctions as a function of magnetic field. And you can see here the cavity frequency is modulating as we sweep the flux. And so if we put an AC flux, if we put an oscillating flux in here, we can actually amplify the motion. So this actually comes a little bit to the sensing applications. So it turns out that these devices can be extremely sensitive detectors of microwave radiation. Basically, if you do your homework right, you can make them detectors where the signal on your network analyzer is 90% limited by the quantum noise of the microwave field. And so that is one application. Now, this is where I came in. There's this idea a while ago to look for dark matter axions. I know very little about this, but to try to push the search for these possible dark matter candidate particles down to lower and lower frequencies. So what I was just telling you about was gigahertz, and the group that I took this picture from, they are actually trying to push it down to megahertz, and that's going to be using something they call a RF quantum upconverter, and that's exactly what we call a photon pressure device. That is going to be I'll try to get to at the end of the talk. But this is another example. This is a paper from a collaborator, colleague of mine, Konrad Lennart, and they've been doing experiments to use parametric amplifiers in a microwave regime to perform quantum limited measurements of microwave photons that come out of a quantum matter detector. And they also use the same device to produce squeezed light to inject into this cavity to increase their sensitivity. That's a little bit, and that's a little bit how I'm wondering how we can maybe connect things that we are working on to this field. So let's see. I'm going to try to then give a brief overview of some of the things that we've been doing in my group. In the quantum sensing activities, I'll classify these into three things. We're looking at quantum sensing of massive objects. We're looking at quantum sensing of RF. We're looking at sensing RF photons, and also most recently looking at quantum sensing of RF currents. So to start, what is the idea of sensing with massive objects? So this is actually an advertisement for a panel discussion I was recently part of online, and there the idea is a little bit that if we can make if we can take things that are heavy enough and make them into quantum superposition, then we could start to try to look at the effect of gravitational fields on the evolution of that superposition. And so we had a long discussion about how this could work and is needed for that. And this I'll show here very quickly an example of what we're doing in my group. So this here is a phononic shield that is isolating the vibrations of a little tiny 20 nanogram mass, which is a membrane in the middle of a 300 micron membrane in the middle of this picture. Underneath it is a superconducting chip we can use to detect its position. And our aim is actually to make this mass into a large enough superposition that in principle we can sense the gravitational field in the evolution of the wave function of that object. But that's
Gary,
yes.
If I may ask.
Yes, of course.
So what is your aim to have the superposition? How large the superposition you would like to obtain in your
our device? Yeah, well, as large as possible, of course. But what we think is feasible for our devices, and that's what we recently put a paper on the archive doing a detailed analysis of this, of how what you could achieve in these superconducting platforms. We think we can displace the object by about 7 or 8 femtometers, and that should. The idea of that is that we can displace the nuclear mass density, out of itself, and if we do that calculation, we can then calculate the way we do this is we follow the ideas of Penrose, and there you can calculate a self-energy of that superposition, gravitational self-energy, and that translates into time. So usually this time is super long. For example, for like a qubit or an atom, this time is something like 10 to the 30 seconds. But because our mass is so tremendously large, the time for our device is something on the order of 10 milliseconds. And the coherence of this cat state we could make should be on the order of 100 milliseconds. And so then we can really try to look for effects of that gravitational energy scale on the coherence of our.
I was curious because you say femtometer, so it's roughly around smaller than even Bohr radius.
Yes, this is true.
But then how do you know it's purely gravity? It could be electromagnetic interaction as well.
Yeah, so the nucleus is also charged, right? So the idea is that you would have to really look at the scaling of this with mass to see how it changes, and it's a little bit of a shot in the dark because we don't really know what will happen. In fact, there's not even a clear idea of what would happen. There are some people that believe that the gravitational field should not be able to carry quantum coherent information, and that should, you know, collapse the superposition we have. And so that's the type of thing that we would aim for. Okay, so I want to show you a couple examples. Well, let's see how much time I have. I think I'm a little bit short on time, come to think of it, but I'll do my best. I'll show you a couple examples of quantum sensing done with these circuits. So the first is quantum sensing at radio frequencies with basically an atom, with one of these superconducting atoms. And there, what we've done, let's say, it's quite common to have an atom which is resonantly coupled to light. This is the whole idea of what Serge Haroche has done with atoms and quantum cavity electrodynamics. And our question was, what if we, of course, if they're detuned in frequency, you can still have coupling. And the question we wanted to ask is, what if you detune them very far? What if this is a gigahertz atom and a megahertz photon? Can we do something with that? And our motivations are a little bit on the idea that our mechanical objects are typically in the megahertz. There are interesting spin ensemble problems. And there's also really fundamental interesting questions like what happens, looking at topics in quantum thermodynamics where KT is not negligible. So it turns out that in second month of his PhD, my PhD student showed that idea on how to do this was completely impossible, and we were off by 5 orders of magnitude in our calculation. And so initially we were a little bit worried about this, but and so we sat around and brainstormed on the whiteboard for a solution. And it turns out that my PhD student had been developing very nice software that allows you to just click around and draw stuff and calculate the quanti-Hamiltonians. It's an open source software package if you're interested in starting to play in this field. And using the inspirations we have from the circuit, we came up with the following idea. The idea is that we have gigahertz. We start with gigahertz photons, which is an inductor and a capacitor, as I've told you. We have our atom over here, which is a Josephson inductor, a Josephson junction, and a capacitor. And we put a huge capacitor in between, really a massive capacitor. This is like the dipole moment that couples the atom to the photons, but it's gargantuan. And it turns out that actually the circuit implements 99% of the theoretical limit of strong coupling between an atom and photons in this type of superconducting atom. And so it turns out that was enough. Of course, when we put this huge capacitor, these frequencies all drop. But what we ended up with in the end, when we analyze the circuit, is a 5.9 gigahertz atom and a 170 megahertz photon. And so this is how we made it. I mean, we have this is a little bit for a feeling of what things look like. We have this printed circuit board. This is the chip we make in the clean room. We go through all sorts of clean room processes to make these multi-layer quantum devices with huge capacitors using dielectrics, these very tightly wound inductors using electron beam lithography, and then these Josephson junctions using this trick of evaporating aluminum inside of a vacuum chamber at 2 angles. So this is what it looks like when you put it all together. This is the circuit. It's very simple. It's just a capacitor, an inductor, and a Josephson junction in series. But that is what implements these 2 modes that I told you about. This atom. This somehow implements both an atom and our photons. And then we have a little wire that feeds, that goes to a coaxial cable that we send microwaves in and measure what comes out. So if we look at this, So so the first thing we can do is we can go and look for our atom. So this is actually where our atom lives. He's about 5.9 gigahertz. And if you just look at the spectroscopy of our atom, you see not just a single transition level, but actually a whole sequence of transition levels of transition frequencies. And these different transition frequencies are us directly observing the photon number shift of our qubit. Basically, because of the RF resonator is strongly coupled to the qubits, and it's not in its quantum ground state at the temperatures we work at. And that means that there are thermal fluctuations. There's about 1.6 thermal photons in the radio frequency mode. And that results in this spectrally resolved splitting of our qubit. And so these are us directly observing the photon, the Fock state occupations of the radio frequency mode. We can actually use this as a primary thermometer, and it's kind of interesting. Actually, it was also very peculiar and mysterious is that our low frequency mode is very cold, but our qubit high frequency mode is very hot, and that's something that's commonly seen in these types of devices. And there's lots of discussions on why that could be. So now, actually, what we did with this next is we wanted to use our atom to do something interesting to our radio frequency mode. So. And what we decided to do is that we can actually drive the atom, and using a sort of sideband transition, a bit like laser cooling, we can actually laser cool the radio frequency mode. And this is a bit different than typical laser cooling, because there's at least in my optomechanics field, because all of these lines are spectrally resolved because of the anharmonicity. But if we drive the system on the correct transition, then this pump can excite the higher level states of our radio frequency mode down to this manifold here, and these all decay. And basically, we're using this driving field together with the dissipation of the circuit as sort of an entropy vacuum cleaner, I like to call it, and that brings us to the ground state with 82% fidelity. What was also fun is we can suck harder with more vacuum cleaners, and that gets us to 90%. And also, it was also fun is we can turn one of our vacuum cleaners around so that it blows rather than sucks. And then we can actually stabilize our radio frequency mode into a non-classical Fock state. For example, a single photon or two photons. Okay, so last I want to touch briefly on quantum sensing with squids. So the idea, sorry, my slides are not very organized, so I'll skip those two slides. But the idea is what I told you before, by putting this loop inside of our device, we can get a device which is very sensitive to the magnetic field. And then the idea is that if we monitor the frequency of this cavity, then we can sense anything that causes fluctuations of the magnetic field in our loop with very, very high sensitivity, in principle down to the quantum level. And that's actually connects to this quantum up converter that the group in Stanford was discussing. And that's exactly what we built here. So what we have is this whole thing here is our squid cavity, which is magnetic field sensitive. You can see it here tuning with a magnetic field. And then what we've done is we've taken an LC circuit and in radio frequency here, about 500 megahertz, and we've run the inductor wire of that circuit right around the loop of our squid. And that means that the currents, any currents in our low frequency resonator will induce flux modulation of our squid, and that we can see as frequency modulation of the cavity. If we're in the right parameter regime, we can actually sense that with quantum limited sensitivity. And then what we can aim to do is to not just measure oscillating currents, but really the 0 point fluctuation currents of this LC circuit running in this inductor. So that's actually something that we've been working on. So this paper here, we showed the first proof of principle of this concept and reached this sort of strong coupling regime. More recently, we used the same circuit to cool our radio frequency mode to the quantum ground state, and that's this paper here on the archive. And even more recently, which we're currently in preparation, we've used this same circuit to now actually sense this current at radio frequencies down at a quantum limited level. And that's sort of a little bit the connection to where we want to think for of new applications in the future. What can we do using the ability to do quantum limited sensing at radio frequencies? So as a summary, I've told you a little bit about quantum sensing in the group, in particular pushing quantum sensing to the limit using these squid cavities and optomechanics briefly. And there are the ideas that we can do force sensing, transduction, and yeah, in some sort of dream of mine, maybe make some contribution to understanding quantum space-time. That'll be super cool. So we can certainly do the experiments, and I'm very excited to get our devices into the right parameter regime. And I've also told you a little bit about sensing quantum things, and then there we were able to use our qubits to actually directly observe the quantization of the electromagnetic field at radio frequencies and stabilize states, non-classical states of radio frequency light. So then I want to end. So this is, of course, all the people that do the real work. This is a picture from a while ago now, long before Corona. I want to highlight a few of the people. So Mario here was the lead on our quantum photonics circuits. Marios and some others also were involved in the measurements. And then Daniel and Ines here are the two people that were really involved in pushing this idea of the squid sensing. And I'd like to thank you for your attention as well.
Okay, thank you very much, Gary, for this very nice overview. I see people applauding and digitally applauding. Good, so there's already a bunch of people who raised hands. Anupam.
I think maybe Joris had his hand before me, so he can go ahead and...
Go ahead, doesn't matter.
Okay. So it's very interesting talk, Gary. So I was quite interested because I myself is interested in testing quantum aspects of gravity. And so that's why I was quite interested in asking you this question. But maybe if I ask you, so what is the coherence, maximum coherence time scale do you obtain in the squids?
Let's see. So it depends on what type in the squid cavities. Let's say, let me push the button again here. Is this going to go from the same slide? Yeah. Okay. So in these devices here, our coherence is not super state of the art. So I think our quality factor is something like 10,000, like 40 or 50,000. And that means that that our coherence time is whatever they're going to be not terribly long. It'll be dissipation rates of some 100 kilohertz or so, I believe.
So if I may say, then these are very good. I mean, so from the device point of view, you have a quantum sensor, but you are actually measuring a classical noise, not a quantum noise. Am I correct?
Well, so so in this case here, so this circuit here, in principle, actually this whole circuit implements optomechanics, and so you can actually understand it completely in the context of this slide I have very early on. If I can zoom back to it, yeah. So so you can understand it in this context here, and so as we turn up the sensitivity of our circuits, then eventually we will hit points where actually the output field of our microwave circuit is limited by the quantum noise of the radio frequency circuit, and that's the regime that we recently achieved in our most recent measurements.
Yeah, the part of the reason is because, as you know, the optical systems are not very good to do very highly extreme sensing because of the decoherence, reasons.
I see. Okay. Yeah,
So,
yeah.
So if you really want to do anything on testing quantum gravity, you really have to give up completely the optical side, and you really have to move to somewhere where you can maintain the coherence. I think I saw somewhere in your plot, NV center or even Rydberg atoms. You put the system inside the Rydberg atom to increase the coherence or map the electronic spin to the nuclear spin.
Yeah.
So if you want the coherence, I mean, because that's the thing which you want at the end of the day, you want to maintain a large long coherence time scale for
Yeah.
any experiment if you want to do.
Yeah, so that's a little bit related to this topic here. I mean, in the microwave, actually the microwave circuits themselves are also pretty damn coherent. So, you know, if you go to, there's an architecture called a 3D architecture, where it's basically a machined out hole in a superconducting you know, piece of metal. And those really get coherence times up to milliseconds now. And we're talking about, you know, like 500 microseconds.
I'm talking about very futuristic, 1 second to even minutes, and minutes beyond minutes.
So actually,
yeah, I'm looking for.
And actually that's, so this little guy here, this little membrane, I didn't have time to talk about it, but that little membrane, this is the mechanical resonator. We want the heavy thing we want to use to try to reach this gravity limit. That one has a tremendous coherence time. But let's say the decay time of that thing is, the one that we measured was 140 seconds. I have a colleague in, that's a Q factor of 129 million.
That's very good.
I have a colleague in Copenhagen who at 10 Kelvin showed 1 billion. And if we combine our scaling to millikelvin with their 1 Kelvin result, in principle, we should hit something like 10 billion quality factor.
That's very good. But how massive can you make them? So that's my
those are also on the order of 20 to 100 nanograms. So
can you go beyond something like micro?
That gets harder. It gets harder. The problem is that in this architecture, the frequency goes down, and then the frequency goes down. You hit boring stuff like classical noise of your microwave generators and vibrational noise of your cryostat.
Great, thanks. Thank you very much.
My pleasure.
Okay, next question from Joris.
Yes, thank you very much, Gary. I had a question. It was nice that we went to that plot that you showed, that one. Yeah. Because it looks a little bit, so I make inertial sensors for gravitational wave detectors.
Yep.
So that's my background at the moment. Well, actually, I did my everything at the TU Delft, but then I got to Nikhef, and then I was doing something else. But anyway, yeah, this looks a lot like LIGO. The difference is that the horizontal axis is the other way around. So we have our quantum back action at low frequency and our shot noise or detector noise at high frequency. But of course, if we omit suspension thermal noise, we have the coating thermal noise in the middle. And if I see your 0 point noise, then that is slightly related to that. So I guess the thermal noise is a kind of flat line that would move there, right? Or something like that.
So if we actually, this is for a 0 temperature harmonic oscillator, which in practice we never have in the experiments. In practice, you actually have an additional thermal noise, which means that this line would not go all the way down, but would then just go across. That makes life a little bit more difficult to reach the quantum noise limit, because you not only need to exceed the detector noise, but you need to actually have the radiation pressure shot noise exceed the thermal noise force. And so that's actually where we typically, it's kind of a funny regime. Actually, this experiment was actually, it actually went from a super hot oscillator, and then with no cooling, they started to heat it like crazy with the laser noise. But if they have enough sensitivity and enough data fidelity with a measurement record, actually they can relocalize it down to the Heisenberg limit, and that's kind of cooling by measurement. It's pretty interesting.
Yeah, I suppose then you can break through this red line or any of those lines with squeezing in the case of gravitational waves.
So that's a very interesting one. I've had a lot of interesting in this context for the squeezing, because the squeezing has the problem of the squeezing will push this line down, right? If you do input squeezing, it will push this line down, but it pushes this line up.
Well, if you do frequency dependent squeezing, in the case of gravitational waves with a filter cavity or other things, you can make the squeezing angle rotate at the frequency that you wanted, and then have the best of both worlds. That's what we are going to do.
Yeah, that could be. So I know that if you just input squeeze, then actually you just shift the power left and right. But that's a very interesting one. Okay, cool.
Yeah. And then the last question, which is maybe possible collaboration, because as I said, I'm making as you said, let's put it that way. As you said, you wanted to look at quantum gravity or something in that nature. And if you can do it in small, but you can also do it in Einstein telescope. So I'm making these cryo superconducting inertial sensors, and I'm using interferometric readout just because I like interferometers, because I'm from the gravitational waves. But we are also looking now at using squids to do that.
Okay.
And I understood you could get a squid commercially with 10 to the minus 14 meter per square root hertz displacement sensitivity, or something like that, at 0.1 hertz. And I would like it like a factor of 10 better. Is it something, a question that I could come knocking at your door for?
Oh, for sure. Yeah, no, definitely. I mean, that's super interesting, actually. So what's different about what we do, the commercial squids are all based on DC wiring.
You do RF.
And there we do RF, and there you have a big advantage because you can use the low noise amplifiers, you can use parametric amplification, and really get down to the quantum noise level, which is very hard at the DC squids.
That's good. Send you an email. Thanks.
Okay, and then the last question by Patrick.
Yeah, Gary, yeah, thanks for a very nice and clear talk. I was actually wondering, I mean, a little bit also related to Joris's question, how you're making all these devices yourselves, right? So can you tell us maybe a little bit more about, you know, the turnaround time and you know, how does this work actually in practice, and how many do you have to make in order to get one that actually works?
So that's a good question. I can give a couple of examples. This one here, right? This is pretty ambitious because it involved a totally new fabrication of a whole bunch of stuff. It involved about 5 months of testing each of the individual components in the clean room. And then actually the first device he made, it just worked and agreed with the simulations to like within 10%. So that was, but it was adventurous in the capacitor dielectrics and the inductor, but the junctions were relatively normal, let's say. This one over here, these guys here, these ones here, we had to develop a new type of junction technology. We have to use, because we wanted a lower anharmonicity, we wanted less nonlinearity. That involved about a year of testing junctions in the clean room. I think my PhD student Ines made about 100 samples. And then, but then once you have the recipe working and you have the in-house knowledge, then turning a sample around after that is like a week or so.
Okay, so you essentially at room temperature, you can do the tests to select one that works, and then you put it in your dilution fridge.
Well, actually, it's more like we do a lot of testing. Actually, once we have the working recipe, then like 80% of them work. So it's more that it takes a lot of prep work. It takes quite some development time to get the recipe working. You always have to check it in a fridge. We have like 4 fridges in the group, for 2 of them dedicated purely for this fast turnaround testing.
Mm-hmm. All right. I also had a question on your quantum simulation, but I'll ask that another time, Gary.
That's fine.
Thanks.
My pleasure.
Okay, is there any final question about quantum simulators, maybe? Okay. Then if not, thanks again for the colloquium. I think it was very interesting. It led to unusual discussions, and I saw already a lot of possibilities for calibration in the discussion after your talk. So that sounds very promising. And hopefully we can maybe see each other in real life for actual lunch, either in Amsterdam or Delft. So so thanks for the moment, and then let's all have lunch by ourselves.
So maybe also good to say, if anyone would like to know more, I'm happy to always chat. So you can, the modern world involves sending me an email, and I can send you a Zoom link, and I'm happy to just chat over coffee or talk a little bit about your research, let's say, or if you want to ask me questions. I'm always open for that. So feel free to take advantage of that offer.
Okay, very good, Gary. Thanks, and Have a nice lunch.
Thanks, Gary.
A pleasure. It was nice.
Great. We'll talk.
Yeah, indeed.